All right, good morning. We are going to be talking about residuals a little bit more and how to find out the actual value of a residual. So we talked about last time that residual is the distance from the actual y value, and that's the perpendicular distance, right? So here we're going to actually figure out how to find the residual. So the residual is found by doing y minus y hat. And this is our actual y value, whereas y hat is the predicted y value. So we say this as y hat, and it's the predicted y value. So let's see how to find that. Now, first, we have a random sample of 11 statistics. Students produce the following data from a third exam score and then the final exam score. And so we're going to predict the final exam score of a random student if you know the third score. So can we? So we want to know, can we use this data to actually form a prediction line? So let's see. So I have 11 scores here, X and Y value. So the X value represents the third exam score, and then the Y value represents the final exam. So this is good as a teacher because if I want to be able to predict what a student is going to make on their final exam. So what I've already done here for us is I've put our X and Y values, if you can see, into my lists and spreadsheets. And I went ahead and did the menu 4, 1, 3. And so I have A, B, and I need that to be F1. And then I want my results to be in C. All right, so if you notice, we get a slope of 2.02, a B value of negative 94.13, and then our R value of 67 or 0.676. So you can see that I did this in Desmos as well and graphed it for us here, same information as well. So this is our prediction line, right? So this is the so what we can do now is we can graph this and see where our predicted values are using the table. I'm going to go ahead and tell you what those predicted values are. It was 69.9, 73.9, 84.1, 84.1, 71.9, 94.2, 73.9, 82, 84.1, 80, and 80. So based on our prediction line, where it was y hat equals our m value, which is 2.02, x minus 94.13. If we plugged in all of these x values into our x variable here, we would get our y hat value, right? So let's calculate our residual now. We're going to get our residual by taking our actual value, 87, and subtracting our predicted value, 69.9. So we're going to do 87 minus 69.9, and that's going to get us our residual, which is 17.1. Seems kind of large. All right, so we're going to do the same thing here, 66 minus 73.9, and we get our residual value, which is negative 7.9. So notice that, figure it out. Notice that if your actual value is larger than your y hat value or predicted value, then your residual is positive. If your actual value is smaller than your y hat value, then your residual is negative. All right, so we can keep going down through the line and subtracting. -5 and -1. All right. So those are all of our residual values. Remember, residual is the distance the vertical distance that each point is from the predicted value, right? So it's calculating that distance. Now, what do we do with this information? Why is it important? Well, we can predict whether this line is actually a good fit, not just by saying the strength, because if you notice our R value is 0.6764, so 0.68, which would tell us that it's between weak and moderate, so possibly a moderate strong, or moderate strong, moderate positive correlation. But what does that actually look like? So we're going to plot the residual values below using the X value for the X-axis and the residual value for the Y-axis. So our X value is going to be on our X-axis, and our residual is going to be our new Y value. And so let's plot this here. And I've put this out as by 3, 3, 6, 9, 12. I know this one kind of goes a little bit far. -3, -6, -9, -12, -15. And then I counted this by 2s, 82, 84, 86, 88, 90, 92, 94, and 96. All right, so I'm going to go up here and I'm going to say, okay, our first point was 81 and my residual value was 17.1. So 81 and then 17.1 is like way up here, right? And then my next point is 83 and -7.9. So 83, -7.9 is about here. 88, +7.9. 88 and -3.1. 82 and -8.9. 93 and 4.8. 83 and 2.1, +2.1. 87 and -1, out here, kind of in all those numbers. 88 and -5.1, out here. 86 and -5. And 86 and -1. Okay, so we can take a look at our outliers here and see, let's look back at our assumptions here. Number one, it has to be the same variance, right? So they have to be the same distance away from the line. So if you notice this one down here, this is a great variance where all of the points are the same distance from the residual line 0, right? Because a perfect correlation, it would have a residual of 0. Here, it does not make a linear trend. So if you look at this one's a great linear trend where it goes all the way across equally. No extreme outlier. This one has an outlier up here, so it does not meet that assumption. And then this one meets all three assumptions. All of the dots are relatively the same distance from the line, same variation, and there's no pattern, right? This one clearly has a pattern. This one has no pattern. This meets all three assumptions. We want our residual plot to look like this. So let's look back at our residual plot that we have made here. And if you notice, we have, see if I can get a pen of a different color. We have kind of an extreme outlier here. And if you notice, in the lower 80s, the dots are farther away, but as we get closer, the dots seem, or as we get increasing in our X value, our dots get a little bit closer to that 0 line. So does this residual plot suggest a linear relationship? The answer is no. We have an outlier. Assumptions are not met. So there's an extreme outlier. And it doesn't meet the same variance. So remember, variance means change or distance, right? Or spread is probably a better word. So we'll use that instead. Spread. They're not equally spread apart. And so here's our other thing that we want to look at. We want to look at our residual histogram. And so I've graphed it here for us. I want to make sure that I'm sharing. Okay, good. Just wanted to make sure that I was sharing this with you. I've graphed our histogram for us, and I just put in our residual data here in our data box. And if you notice, it's very right skewed. So it does not meet our normality assumptions for our histogram. So does not meet our normality assumption. So we can say on our plot here that our histogram of residuals is not normal. So even though we have a moderate positive correlation based on our residual values, we really can't use this linear trend line to predict final exam grades. It would be very loose. And if you notice here, this 45 or 0.4575, only 46% of the data values can actually be fit to that trend line. So it's kind of a low number. All right, let's turn it to the back and see. Here's some U-try questions. We're going to complete each table using the given linear regression, and we're going to round each answers to one decimal place. So I have plugged this into our Desmos graphing calculator here, if you notice. So it says y equals 0.5x. You can also do this in your calculator. And we're going to plug in our predicted value. So here's the actual value, and the predicted value is what's going to be on this table here. So for 5, our predicted value is 2.5. For 10, our predicted value is 5. For 15, our predicted value is 7.5. And for 20, our predicted value is 10. 25 is 12.5. And then 30 is 15. So I've written those predicted values here on our piece of paper. Now let's find our residual value. So our residual value is our actual value 3 minus our predicted value 2.5. So our residual value is 0.5. 4 minus 5, and our residual value is -1. And then 9 minus 7.5, your residual value is 1.5. 7 minus 10, -3. 13 minus 12.5 is 0.5, and 15 minus 15 is 0. Remember, when you have a residual value of 0, that means it's a perfect match, right? Just like our compatibility. So let's graph, and I'll actually walk you through this. Our X values are great right here because it's perfectly spread apart for us, 15, 20, 25, 30. And then it's from, oh, sorry, residual value. I'm going to say we can probably do 1, 2, -1, -2. Help us see it a little bit better. So if our X value is 5, our predicted value is 0.5. So right here. When our X value is 10, our residual value is -1. So down here. X value is 15, residual value is 1.5. And then X value is 20, residual value is -3. So it's way down here. And then X value is 25, residual value is 0.5. And then 30 and 0. So does the linear plot suggest a linear relationship, a residual plot? And I'm going to go back to one of our assumptions here. This looks like an extreme outlier, but let's look at our histogram too to see if the histogram meets the normality assumption. And I've graphed it here for us in our StatsMedic applet. And you can see that it's quite left skewed. And you can even look at the box plot and notice how the median is to the right. And there's so much space here on the left. And you can also look here down where your mean is -0.25 and your median is 0.25. Those are quite far apart. So I would say number 1, no. And which assumption does not meet? Does it not meet? Does not meet extreme outlier assumption. And the residual histogram is not normal. What did we say? It was left skewed, right? Yeah, left skewed. All right, so now it's your turn. If you want to use Desmos and plug these into your calculator, you have 2 more to try on your own. Go ahead and try these, check them with me at my desk, and then you can move on to Delta Math.